Hi. So, in this series of videos, I want to discuss analog computation, which is a subject that I've recently become very interested in, both as a means of learning about electronics, learning about mathematics, solving differential equations. But it's also, I think, a technology that's going to be very beneficial in the future for those of us that do engineering and physics and any sort of numerical computation. Okay. So let me begin. Okay, so I guess there's a couple ways I could go at this, but I'll just go ahead and start off, what is computation? And I'm going to simply, using a machine or mechanism, solve a problem. That's quite broad. This could be by machine or mechanism. You think of a desktop computer and a personal computer. But what we'll see is computation. Solving a problem can actually you can do this using a variety of different kinds of machines and different kinds of mechanisms. And by problem specifically, we're gonna in this case talk about differential equations. So, and what we'll be solving today is just a very simple differential equation given here. Now, I'll start off here solving it analytically, just on pen and paper. But what I want to show how we can solve this using an analog computer. Now, I think a good place to start is just to go ahead and solve this, get an analytical solution, and then we'll talk about kind of how you might do this with a digital computer or some sort of numerical scheme, and then we'll talk about how you would do it with an analog computer, and then I'll show that. So just quickly solving this, we can just solve it by separation and integration. So we'll separate each variable on each side, integrate it here from x naught to x, on the right hand side from time 0 to some time t. This gives us the natural log of x from x naught to x is equal to minus a t from t naught, which is equal to 0 to t. I'll go ahead and just solve this all the way out. Okay. The difference of logs is the same as taking the log of the first term divided by the second term. And then we can eliminate the log by exponentiating both sides. So x over x naught is equal to e to the minus at. And then just to isolate x by itself, it's x naught times e to the minus at. So we're going to start with some initial value, and then this is going to exponentially decay away at some rate determined by this coefficient alpha. And a real world problem, this differential equation describes a large number of real world problems, such as radioactive decay, I guess ion beam attenuation when it passes through a medium. Many things are describable. Population dynamics are describable by this equation and similar. And we solved it here with pen and paper, but an alternative would be to use some sort of, approximate numerical scheme. So this is what I'm going to show is not how you would actually maybe do it. This is quite a bit simplified, but I think it'll get the idea across. So starting with the differential equation, okay, what we'll do is we'll do a series of approximate steps. So we'll now approximate, instead of solving for dx dt, we'll solve for a delta x over delta t is equal to minus ax. And so we can move over that delta t to the other side. Let's see here. Okay. And what we can do is if we kind of imagine a plot here, let's say this is time 0, here's 1 second, 2 second, 3 seconds, so on and so forth. And then we have x. Let's say we start at the initial condition is just an x of 1. We can basically just approximate some step and then keep approximating forward. So let's see here. So if I want to get my delta x, let's say I have a delta t of, we'll just say a delta t of 1. Then a, again, I'm just going to make this easy. I'll say a is equal to 0.1. Okay. So then x here, delta x, we'll use basically where it is at the first time step. So at time 0, it's at 1. So that would just be delta, the change in x is equal to minus delta. And I'll make a little table here. So if we start at 1, our delta x is just going to be, okay. So with this solution, with this we have this analytical solution. Now we want to maybe know, how can we solve this using a computer? So with a digital computer, you could use something like an Euler scheme, a forward Euler scheme, or an implicit scheme, basically where you're going to approximate a solution. Now that approximation can be incredibly accurate, but with a digital computer, you would do basically a series of, you would develop an algorithm that would have a series of steps. So while the next, what I'm going to show next may not be, it's not exactly how you would set it up. I think it's at least decently representative. So what we would do is instead of, let's imagine, I'm going to go ahead and make a plot here of t on the x-axis and x on the y-axis. And we're going to have some initial condition of 1. And what we can do is we can take, instead of solving the equation exactly, we can have some approximate. So I'll have delta x over delta t is equal to minus a times x. And what we'll do is we'll just approximate the next x given where x is at the moment. So let's see here. So delta x is, if we expand that out, is a x nu minus the sub n, I'm just going to say nu. So x nu is equal to xi. So that's going to be where we are now over top of delta t is equal to minus a times xi. Okay. So yeah. So if we solve this, so delta t we'll set the time step to be something like, we'll just say it's 1 second. So we'll calculate a new x after we take each new step. So then if we solve just for x new, is going to be equal to minus a times xi times delta t plus whatever initial x it is. So we can kind of think of this as this is going to approximate the solution, and it will be more accurate if we make delta t very small. So how would we do this? So let's just give some values here. So we'll make a equal to 0.1, and we'll take a step every second. So if we want the first x new is going to be equal to, let's see here, the first x new would be equal to, just going to be equal to x initial, which is 1, plus minus a xi delta t. So that's going to be minus a is 0.1, xi is 1 for this term, and then delta t is going to be 1. So that's pretty easy. It's just going to be minus 0.1. So our first x new will just be 0.9. So if we, let's see here, 1, 2, 3, 4, 5, 6. So about here is 0.5. Here's 0.75. So I'll put 0.9 to be about here. And we can just draw a straight line between them. Then I'll use this as my new xi. Okay. And then redo this calculation using that as the new xi. And what you'll see is if you have too large of a time step, this will become quite inaccurate. And as you limit to smaller time steps, you'll get the correct solution. So this is, without going into a lot more detail, maybe I will in future videos, but this is kind of how you might think of a digital computer is going to handle the problem. It's going to not solve the exact problem. It's going to actually be an approximation of the problem, and then it's going to repeat a series of, it's going to repeat an algorithm to do this. And all the while, the digital computer has to continually reference storage values. So for this, not a big deal, but for much larger problems, that can actually become the bottleneck and cost a lot of energy. So how would an analog computer handle this solving this solution? Well, what we mean by analog is that we're going to actually assemble a machine that is described by the differential equation we care to solve. So I'll just rewrite that down. So in our case, the machine is going to be several electrical components. Now, the machine will be a series of electrical components that mimic this, or I shouldn't really even say mimic, are described by this set of equations. We're then going to let that circuit run, and we're going to measure values of that circuit to get our solution. So we're not actually really approximating it. We're actually physically instantiating this mathematical problem. Now, I won't, in future videos, I'll go in, I think, kind of as I learn it as well, kind of more the details of the circuit itself. But from a kind of slightly abstracted view, we can have what's called an integrator element. Now, this is an op-amp, and this is an op-amp series of resistors, transistors, capacitors that will integrate any voltage that you put into it. So if I pass some signal, which is going to be have a voltage, and it's going to represent my x, it's going to give me the integral of whatever signal I pass in. So if I give it x dot, which is the derivative, remember x dot is just defined as dx over dt. If I give it x dot and I pass it through this set of circuit elements that is represented by this signal, it's going to output a minus x. And now the minus just comes from sort of the, how should I say, the minus x comes from kind of, it's sort of an artifact of the circuit elements. But what we can do is we can then multiply by some coefficient value here, which we'll call a, to now get minus a times x. And then we're going to go ahead and feed that back into the integrator. So what we've done is we've wired together, and then again, this is kind of abstract, I'll show in a moment, but we've actually wired together a circuit element that exactly describes this differential equation. And what we need to do is, we don't care about minus x, we actually care about x. So we'll branch off of this point here. We'll branch off of this point. We'll invert it from minus x to x. And then we will measure this with an oscilloscope. which I'll show in a moment. Oscilloscope. Okay. Now, every circuit, like we saw, every differential equation needs some sort of initial condition. So we'll also initialize it with an initial condition x naught. So what have we done here? We're going to take some circuit components, wire it together. This circuit itself is well described by the differential equation, and then we're going to run the circuit, measure the circuit, and use the output measurement as the solution to the set of equations. So why would you want to do this? Well, if you were just trying to solve this problem, it would be a lot of work for not a lot of gain. However, what we'll see is that this circuit requires much less power than a digital computer to solve the same equation. And as we go to more complex problems, the analog computer should be able to outperform the digital computer. Now, what is the trade-off? The trade-off is definitely it's a different way of thinking of trying to solve the problem. And then there's actually much more limited accuracy. So like I said before, with the digital solution, kind of represented by what we did on the right side here, the digital solution, you can get to the accuracy of the machine. So the accuracy of your digital computer, which can be, it's 0.0000, so on. It's many digits of accuracy. While the analog computers is somewhat limited to something like 2 or 3, probably about 3 digits of accuracy. And that can matter or cannot matter. For a lot of problems, that's within the accuracy that you need to understand what's going on. But for other problems, it'll cause issues. So we'll go into the kind of pros and cons of these computers in a lot more detail in the future. But let's go ahead and, I guess, switch over and actually wire one of these up and kind of make it happen. And here, I'll just take a quick break. Pretty much everything I'm going off of is from this textbook here, which is really excellent. It's Analog and Hybrid Computer Programming by Bern Ullman. I highly recommend looking up their videos that he's made. He can do a much better job explaining it than me. But this is kind of the reference text that I'll be going through, and specifically this problem is given in more detail on page 49 of this text. So now I'll go ahead and switch over to the DocuCam, maybe. Okay, so shown here are 2 different analog computers. So this is on the left here is the analog thing by the company Anabrid. And this is sort of a classical analog computer in that it has a patch board. So this is where we're going to sort of program our analog computer. Basically, we're going to wire together the circuit itself. And then here, which we won't go over today, but I will in future videos, this is just this is an Okika, it's called a field programmable analog array. And that it does very similar to what this computer is doing. There's just no patch cable. You implement the circuit that you want via software. These four kind of chips, right? 1, 2, 3, 4. These 4 chips have all of the circuit components, in a solid state integrated circuit with a reprogrammable kind of solid state patch cable. So yeah, and then in the future we'll also use just through remote login, we can submit problems to Anabrid's more powerful REDAC computer, which is a modern and more functional analog digital hybrid. Okay, so what's going on here? Each of these smaller blocks, and I'll kind of raise this up to the camera so it's a little more, let's see here. Okay, so what's going on here? I'm going to try and bring the camera a little bit closer. So each of these sections is a different electrical component that has some sort of mathematical operation associated with it. So up top here, we have integrators, and you always have for the integrators, you have an input, you have an output. So you pass the signal into it, it integrates it and passes it to the output. And then you also, the initial condition that you're going to initialize that integration with. We have summers, so we take 2 signals and add them together. We have an inverter, which again, some of these integration is one that actually gives the negative of the output signal. So if we might need to invert it before we pass it, somewhere else. And then we have 2 multipliers, so multiplying 2 signals, and we have comparators and a few other, kind of options, which we'll go maybe in future videos talk about. And then along the side here are our programmable coefficients. So in our problem here, we had our dx versus dt is going to be equal to some minus ax. So we want to be able to represent that coefficient and adjust it. So that's what these values over here are. So we take an output signal and pass it through this one. It's going to multiply it with some coefficient value. And then we can adjust those coefficient values with these knobs over here. So we have 8 coefficients, and then this is just a coefficient selector, which allows you to, so if I turn this on to coef, go to coefficient selector, I can see what the actual values are at. So if I want to specifically set it to some, between 0 and 1, here you go. I can try to get it close to 0.7. And again, this is sort of, I mean, this is already showing to a certain degree, kind of limitation of analog computers. That this board here is really more of a learning tool, and is easy to learn a lot of the concepts of analog computation. But something like this is what you would actually use to solve a real problem. You would program this using, like you would reuse a regular digital computer to write a programming file, which this company has the software which would compile it into something that these smaller chips can understand. And this is really a hybrid computer because right underneath that it attaches to is just a Raspberry Pi. So the analog computer is going to solve the differential equation, but the storage, programming, all of that is handled by the digital computer. And then down here, we have 4 outputs. So we can measure 4 variables at a time, which then come up to here, which are these audio jacks, which then go to an oscilloscope. So this is just a cheapy kind of, this oscilloscope attaches to my PC, and in the future I'll get a nicer oscilloscope, so it's more fun. But we can just get our 2 signals on here, A and B signal, which then is read in software, which I'll show here in a little bit. So the plan is we need to wire together. We have to wire together on this computer this circuit, which is going to be very simple. So I'm going to do this. I try to do a tripod setup. I'll get a better tripod in the future that can help with this. But I realized it's a little difficult, so we're just going to have to deal with my hand being the tripod. But so we have some output here. Remember, this is going to be our minus x signal, and we're going to need to attach a coefficient value to it, so minus a times x. And then this will be coefficient 1, and that becomes our circuit. So it's that straightforward. It's a very simple circuit. It's closed, so that kind of the thing to realize later is that all your integrations have to be closed. It's the feedback that gives, allows the circuit to evolve towards its kind of final solution. But what we're still missing, of course, is we have to have an initial condition. So in our case, we'll start just with a +1, and I want to be able to kind of change around what the initial condition is. So this will be coefficient 2, comes in here and gives us our initial condition. So this +1 is just a +1 value of the voltage from the computer, and then we'll be able to modify it with our coefficient number 2 here. Okay. And then let's see here. Yes. And then we want to be able to measure this, right? So remember that this is going to be a minus x on this side. So we're going to need to invert it. So we'll take another output from there and we'll come over and just invert it here. And then we'll push it to our oscilloscope signal from, let's see here, from +x. Okay. All right, great. So there you go. This is kind of your bare minimum, analog computation. Some other details is our op time. So this is a function with respect to time. So this is how far into the future we're going to integrate it forward. So we can go to some maximum, basically. We can't go to infinity. We go to some maximum, and then there's a couple different options, but I'm just going to go to rep F. So this is going to be repeating. So we'll see several repeated. I guess it'll make more sense when we see the oscilloscope. So let me just show that here. Okay, I'm going to move the camera back. Okay, attempt to move the camera back. There we go. Okay, so you'll at least be able to see my 2, coefficients changing here. And then now I'm going to share my screen and move over to the oscilloscope. Okay, so and I accidentally, I plugged this to the wrong output. Okay, so here we are. This is, how should I say this? This is what the analog computer is actually outputting. So if we zoom in just to a single kind of time trace here, you can zoom in, zoom out. It's much more satisfying using a real oscilloscope. This kind of computer oscilloscope's a little, I don't like having to use it with, and see, I lost it. Let's just do an auto setup. Here we go. All right. So here's the signal. Remember that rep F. It's just repeating. It's basically the analog computer itself has some signal generator that then is getting passed through this series of circuits which we've wired together to give us the solution. So if I remember, our first coefficient is the rate of decay. So if I make it small, it takes a lot longer for the signal to decay. Or if I jack it up, it increases the intensity. And then the other coefficient 2, was our initial condition value. So I can go a higher initial condition and increase the rate of decay. I can go to a lower initial condition and change the rate of decay. So all this is to say, by means of a different kind of machine, we've solved this problem. And it's because in the case of the analog computer, the circuit which we've wired together is well represented by the same differential equation as the problem we care about. Now, the last kind of thing, and this is a tricky kind of a tricky element to the analog computation, is that we have to scale the problem appropriately. The analog computer can't run over kind of an infinite time, and it has limited voltage values that it can actually represent, right? So you as the programmer have to decide, what is 1 volt represent in the real world. So you might have, if you're trying to describe a, let's say, radioactive decay, and you start with 1 kilogram of the material, you might have to come up that 1 volt equals 1 kilogram as sort of your scaling relationship. And that would tell you, when you try to interpret this output signal, you could tell what it, represented. Furthermore, the coefficient A that we had, you need to figure out the analog computer has some time that it's going forward, but you need to also scale what that time represents. And you do that by appropriately picking the A constant. So there's still definitely some more work on the end. And this being a traditional analog computer, I'm getting this solution, but there's still more work to be done. I would need to save this solution, and then I would actually need to, I guess, analyze this, presumably using a digital computer. If this is my solution to the problem, I would need to pull it out and then analyze it just with a regular, analyze it using some kind of fit it with some least squares function to get what the A is, or excuse me, to get how X is behaving over time. So yeah. I guess this is kind of maybe the end. Hopefully this was not too torturous of an explanation, but this is kind of the most straightforward problem we can solve. In the future, I want to solve more complicated differential equations, and then eventually we'll move to using some of these analog digital hybrid systems where we can start solving, actual problems. Okay, thank you very much for listening.